I'm very pleased to be here today. Thank you for the invitation to be part of the NAVAt program. I love talking about engineering, so that's no problem, and it's even better to be here with so many good friends over many years, and beautiful venue, and thank you, and look forward to today's busy activities. I would like to start with a little bit of a historical perspective of what our workshop today on automated low flow and visual drug displays is all about. 40 years ago, the Society for Closed Circuit Anesthesia was sort of at its prime, very active. At that time, Harry Lowe and Ed Ernst published their book on the quantitative practice of anesthesia, the use of closed circuit. In those days, they were using a closed circuit. In the closed circuit, the patient's exhaled gas moves into the bellows of the circuit. When the bellows is depressed, the gas moves back through the CO2 absorber and back to the patient again. In closed circuit anesthesia, there's no vent, there's no leak out of this closed circuit. Because of that, the volume needs to be controlled and kept constant so the bellows is full. That's done with a feedback control that introduces nitrous oxide and keeps the reference volume at its desired level so the circuit remains full so ventilation can be maintained. Of course, it's also critical to keep the oxygen concentration constant in the circuit. So the desired inspired concentration is entered in, and a feedback controller then controls the delivery of oxygen to keep that circuit filled with the desired oxygen concentration. And in the practice of closed circuit, as promoted by Harry Lowe especially, the anesthetic agent is introduced via syringe in unit doses based on the patient's weight and requirements. Unit dose is given at each period of the square root of time. So at 2, at 1, at 4, at 16, and 35 minutes, another unit dose is given. This is a very simple and straightforward way to use a closed circuit and get the best economy of both your gas and agent delivery. Over the years now, this closed circuit has been enhanced by the introduction of gas monitoring, where the inspired or expired end tidal concentration of the anesthetic agent is measured, and that signal is compared with the reference to a gas delivery system, the DIVA by Draeger, into the closed circuit. And now you have the closed circuit control of both oxygen, nitrous oxide, and anesthetic agent. So over the years, automation is brought to bear in the use of closed circuit anesthesia. And as we just heard from Professor Montier, to be harmless, Draeger added a supervisor, a second sensor independent of the first, to supervise and manage the system. So we now have today available for our use 3 anesthesia machines that use the closed circuit and low flow or closed anesthesia. The Zeus from Draeger, the Felix, and the GE ACES all have this automatic closed loop control, automation of the gas flow. What I feel is still missing, though, is these machines do nicely at controlling the end tidal agent, but what we're most concerned with is the cerebral or the brain concentration of the agent. And thanks to Jim Phillips, I did a simple simulation using GasMan. In this instance, we started with an isoflurane concentration of 5%, held it there for 2 minutes, and then went to 1.2% inspired concentration. And you can see here the rate of rise of the inspired concentration, the rate of rise of the end-tidal concentration, and that combined brought the brain concentration to the target level in less than 3 minutes. Very rapid controlled induction. This did happen at a high fresh gas flow or rapid ventilation and a high cardiac output. Induction is not nearly that fast if we don't have these sort of prime conditions. So I think as we talk about drug displays and the use of senior drugs at work, it will be important in the future to plot the brain concentration. This is our target value. We should see it and should be displayed. We've enjoyed using Yash LaRue's model of anesthetic uptake as shown here, which will produce a measure of brain concentration. In this model, the input is the fresh gas flow, and the vaporizer setting goes into the breathing circuit, where we then have a measure of the inspired concentration. In the alveolar space, we get a measure of the end-tidal concentration that is picked up by the blood and flows to the various tissue compartments, one of which is the brain. So wouldn't it be nice in the future if this model were running in the background, as Professor Ikeda used in Hamamatsu, where you measure end-tidal concentration of the agent, put that into the model, have a non-invasive measure of cardiac output. We measure end-tidal CO2 to compensate for cerebral blood flow changes that happen at different CO2 levels. We would then get quite a reliable measure of brain concentration, and we could display that in our anesthesia machines. I'd like to now move to the intravenous drugs and the work that's done there to show the kinetics and dynamics of these drugs. To capture the amount of drug delivered, we can use a computer interface to the infusion pump to capture that rate of delivery. With the drugs that are given in a bolus via syringe, DocuSys is one example of a camera behind the syringe that measures the barcode on the syringe to tell you which drug it is, measures the volume delivered, so you capture that information. There are currently other systems being developed that may do that even more efficiently. The barcode syringe information and the infusion pump information is entered into a pharmacokinetic model, 3-compartment model that calculates the central compartment concentration and its distribution to rapid and slow peripheral compartments and to an effect site. That effect site concentration can then be plotted as we see in the Draeger Smart Pilot, where we have the propofol, remifentanil, and the neuromuscular drugs shown with the effect site concentrations plotted versus time, showing the rate of rise and fall, and then a prediction of future concentrations in each of at the effect site for each of the 3 drugs. And the Smart Pilot also records and displays the BIS on the same timeline, the processed EEG, so that you can begin to compare the physiologic response with the effect site concentrations. To calculate the pharmacodynamic response of the patient, how are they responding to those effect site concentrations? If we plot the effect site concentration of remifentanil and the effect site concentration of propofol on this 3-dimensional plot, we can see with the administration of the bolus of remifentanil a rapid rise in the effect site concentration, and then as propofol is given, you begin to climb up on this surface till you rise above the point where the probability of not responding to algometry is at 50% or 90% probability of not responding. Algometry is a pressure piston placed on the tibia, on the shin bone, and at 50 psi represents a stimulus that's quite equivalent to postoperative pain. And this is a colonoscopy where the user took the concentration up here to about maybe an 85% probability of not responding to algometry, which was sufficient analgesia to block the response to colonoscopy and result in a comfortable procedure for the patient. Talmadge Egan at our place would like us all to see these plots because it contains the most rich information we have available on what the effect site concentrations are doing to the patient. Oops, I went the wrong way here. In the Navigator, I think they're on the Smart Pilot, this is Draeger Smart Pilot display, they have introduced that response surface in a two-dimensional form and have simplified it to make it more accessible to routine users. As you see on the right, they're plotting the effect site concentrations for each of the drugs. And then on the left is shown, let's see if I can go back now. Great, thank you. On the left, the effect site concentration for remifentanil and fentanyl are shown on the x-axis, and the effect site concentration of desflurane and propofol are shown on the left. These are on the x-axis. And so these are now the response surfaces in two dimensions with bands for adequate anesthesia and light anesthesia. And currently, the total pharmacodynamic effect is in this dot in the center, showing it's halfway between adequate and light anesthesia, with the projection into the future shown by the dotted line. So this gives the clinicians access to those complex pharmacodynamic relationships in a very simple and user-friendly manner. Shown again here are the effect site concentration for remifentanil equivalents and effect site concentration of sevoflurane. The patient is currently at this point with quite adequate anesthesia and headed in 10 minutes to the point of light anesthesia. This is quite an elegant, simple presentation of those complex pharmacodynamics. And I think we'll hear later today how useful they are clinically because of their simplicity. The available models and information we have are shown in this slide, where the volunteer studies have produced response curves, pharmacodynamic response curves for consciousness, for response to laryngoscopy, algometry, that's 50 psi on the leg, and then tetany is electrical stimulus. In the Navigator, as opposed to the Smart Pilot, these first three response curves are used and integrated into the display as shown here. So the effect site concentrations are the input to the pharmacodynamic model, and then based on where the patient is, we can then plot the probability of response to laryngoscopy and the probability of response to a painful stimulus, plot those concentrations versus time, and predict the concentrations 10 minutes into the future. So we can see on the right that the probability of a response to OAS or to consciousness is far above the 95% probability of response. So the patient is clearly soundly asleep because of the contribution of propofol, fentanyl, and remifentanil, and then the synergy between the two are shown here. We found in early human factor studies this display on the right is a little too overwhelming, a little too complicated. So for the anesthesiologists in the United States who are really unfamiliar with effect site concentrations, where the smart pilot would have difficulty because we're just not used to TIVA and thinking in terms of effect site concentrations, the NAVAgator displays the pharmacodynamic information as a function of the probability of unconsciousness, where the top line is there's a 99% probability of unconsciousness. You can see the contribution of propofol alone to that probability, and then the synergistic component takes the total probability of unconsciousness to well over 99% at the beginning of the case, and then 10 minutes into the future will be about 97% probability that that patient is unconscious. For the probability of response to intubation, the drugs were delivered to produce a probability of well over 95% probability of no response to laryngoscopy at the beginning when laryngoscopy occurred, intubation occurred. And then now the concentrations are headed down to where at the end of the procedure, the probability of response to postoperative pain as measured by the algometry surface is shown here with 50 and 95% probability of not responding to postoperative pain. So the anesthesiologist can control the future of the system using the NAVAgator display. It's clear that prediction into the future is a very significant component of both the smart pilot and the NAVAgator. If you look into the literature, the thing that makes our high-speed military aircraft controllable is the prediction of where that plane will be in the future. Without that prediction, it's just so difficult to control a plane with that much power and that much speed. So it's very common in the navigation displays to have a follow-me airplane that shows where the plane is going to be. And this is what makes all control systems easier to manage and maintain. So that prediction into the future is perhaps the most significant contribution of both of these displays into the making it easier to control and manage anesthesia. This is the implementation of the pharmacodynamic display in the GE NAVAgator. Oops, I did it again. So you can see the right in the center the plot of probability of unconsciousness, the probability of response to laryngoscopy, and then the neuromuscular blockade. That is found on an auxiliary display to the GE ASIS machine and plots those variables right here. We also see other information that in my mind sort of clutters what we thought was a very elegant display to begin with. We've got the disclaimers from the manufacturer about questioning the value of these projections and why they may or may not be right. We've got the anesthesia record with drug information here, a lot of other buttons that, in my sense, make it, the information's still there, but it's somewhat cluttered. And I'm a big believer in Tufte's work and keeping it as simple as we can. I would like to just mention then a few of the strengths and weaknesses of both the NAVAgator and the smart pilot, and be careful in understanding what I say, because I do have a conflict of interest that I must disclose being involved in the development of the NAVAgator. But I see the strengths of the NAVAgator in the separate displays of sedation and analgesia. We use different drugs to control both. So it's important to have both displayed so that you can manage them. And I'll show later in some of the results that it's made a difference in how analgesia is managed during the case because the separate display of sedation and analgesia rather than adequate and light anesthesia. Predicting drugs to the future is very significant. The weakness of the navigator approach is that this probability of response is somewhat of a foreign concept. Users need some time to understand it and be able to use it effectively. How to adapt these models for individual patients is still unresolved. The navigator does not show the processed EEG alongside the information on drug kinetics. And then the prediction models are not as transparent as they would be if we showed the entire surfaces. And the navigator, as I understand it, is not primed as well for automation. In the Draeger-Zeus machine, you have a bank of infusion pumps that are all interfaced and easy to control, and that would be an advantage. The Draeger implementation of the Smart Pilot is shown here. It's very nice to have the same time axis to show effect site concentrations for the drugs that are being delivered. Very useful, especially in Europe, to show those effect site concentrations as a function of the bolus of drug and the infusion rate, to plot that very clearly and predict it into the future. And it's nice to have the hemodynamics, should there be a response there from inadequate analgesia. It's nice to see the processed EEG, the BIS, as a measure of consciousness, and then a measure of nociception plotted all together. Very nice, elegant display on the same time axis for managing these drugs. And then on the left, of course, we have the more simplified display of a surface with adequate and light anesthesia and a projection of where the patient's going there. The strengths of the Smart Pilot then are prediction of the total anesthetic effect that's simpler to use. The response surface is more transparent because it's shown in the display, and the transition to automation is all set and ready to go. I think one of the weaknesses would be that the analgesia and sedation are more difficult to manage because they're not shown separately in this display. So I'd like to take a minute now and talk about the human factors evaluation of the displays and how they have been useful. What value can we claim from using these displays of kinetics and dynamics? Noah Syroid did a study in the simulator where he simulated a orthoscopic procedure in the shoulder, which produced levels of pain that were quite intense during insertion of the scope during the procedure, and then the surgeon decided he needed to open the shoulder and do a more invasive Bankart procedure. There is the skin incision with even more intense pain, and then through the procedure, the pain level was up high and then dropped down at the end. Those users in the simulator that use manual control during this procedure were somewhat surprised with the intensity of the pain stimulus at this point, gave quite a large dose of analgesia to bring the probability of response to analgesia up perhaps higher than needed, and continued to keep that higher until the end. The users that had available to them the pharmacokinetic and dynamic displays tended to give more frequent bolus doses of the drug, and they maintained the total level of analgesia lower than did the control group. So I think two demonstrations of how clinical practice was changed because of the use of this display. In a recent study with 30 patients, and this will be published soon, we found that At the end of the procedure, when surgery had ended, we show here a plot of the effect site concentrations of fentanyl on the x-axis and isoflurane on the y-axis. So you see that the total effect site concentrations at the end of the procedure for those anesthesiologists and residents who used the drug display were shifted to the left and higher than those who used the pharmacodynamic display. These are the probability of response to 95% probability of loss of consciousness, loss of response, conscious response, 50% probability. So this represents now a change in practice where those that used the display ended their procedure with more fentanyl or analgesia on board than isoflurane. They tended to protect the patient at the end of the case, anticipating postoperative pain. And as a result of that, this shows for the display and for those that did not use the display, there were 15 in each group. Those that without the display received more fentanyl in the postoperative period. So patients were asking for pain relief, received more pain relief because they were not prepared as well for the postoperative period. And the introduction of the display then may represent a change in practice in that the patient's our postoperative analgesia is managed better.
May I ask you to come to your conclusions, please?
Sure, will do. The prediction of probability of time to wake has been confirmed. There is a 1.5 minute difference between when the patient actually woke up and when the drug display predicted they would wake up. And the users were quite satisfied with the display. This shows a self-assessment of performance, frustration, effort, and mental demand. And when the drug display was used, these measures favored the use of the display. And our residents and anesthesiologists in the latest study report that they perceive that the drug display's prediction of return of consciousness is a better prediction of when the patient actually awakes than is the processed EEG or their own self-assessment of time to awake. So, and then with the theme of being harmless, they report that when they used the display, they were not distracted or in any other way prevented from using their skills as they normally would. So the display, in fact, was doing no harm as it was used. In conclusion, then, I think what we still need and what's still missing is a sensor for the end-tidal concentration of propofol, the blood level. That would help significantly in improving our models. A measure of analgesia would help us adapt the models for each patient. And then I'm happy to report that Kai Cook, the engineer who was the brains behind much of the smart pilot development work, has now joined the group in Utah where the NAVAgator was developed. So we have Kai Cook there to take advantage of both of these displays and hopefully move the work forward even further. So, thank you.